It gives me insane pleasure to introduce a mechanical engineer. And James Petersen is very unusual for a mechanical engineer. He has a personality. I can say that. I'm a mechanical engineer, all right? So we're kind of blood brothers, except nobody else understands us. James is, in my opinion, the go-to mechanical engineer and mechanical systems that I would ever trust. I'm serious. James keeps us out of trouble. James fixes things that are broken. James designs things to make sure they're not broken. And are you ready for a bad joke? Size matters. You're never going to hear this from most people. Smaller is better. So please give a warm welcome to James Petersen.
Thanks, Joe. Appreciate it. Thank you, Joe. So last summer, after summer camp, I thought to myself, you know what? I'm going to pitch a presentation idea to Joe. And so I went right up to him. I said, Joe, you know, I think I've got some things to present. I'm funny. And I thought maybe he'd say, you know, maybe next year. He said, okay, you're on. And then I've been nervous ever since. I thought he'd give me more time. All right, so I have a few passions other than HVAC. So I'm going to show you a few of those, and then we'll get into HVAC. I'll tell you a little bit more about me and my company here. But we're going to start with something to wake everybody up since it's 3 o'clock. We're going to, you know, it's got to be chainsaws, I think. This is one of my passions. Hopefully we got audio. All right, we're going to start over. Audio? Thank you. I think I'm trying to set up the iPhone here to take a video. Yeah. Never cut down a tree by yourself. Exactly. I'm still here. So you know I don't die in this one. So I really enjoy cutting down trees, but I just learned that the next best thing is watching yourself cut down a tree. I don't know if everybody else liked that. I really enjoyed that. Carmen. Jokes. Yep. Longest bar, 36-inch, right? I learned a long time ago that you really want the bar to be a little too long rather than a little too short. So yeah, always make sure the bar is longer than the tree is in diameter. So so my presentation is titled smart, let's see, no, not smart, small, simple, serviceable. So, or smart. And so the professors this morning were talking about simple and doing that right. So I think I'm on the right track. We'll see. So a little bit about my firm. We've been around a long time, since 1992 in Portsmouth, New Hampshire, which is about 50 miles north of Boston. We have 20 of us. We have good representation here today, some of my colleagues, about 20 people. And we are MEP FP engineering firm. And so what I'd say about us, we're super efficient. The amount of work that my crew has done over the years is really impressive. So I do want to tell a quick story in how we got into multifamily. It's not everything we do, but it's a lot of what we've done since 2008. And how that happened was someone called Betsy Pettit and said, "You know a good mechanical engineer?" And from that time, we have since done we've been the engineer of record for 26,000 units of housing, mostly in Massachusetts. The other thing I'm super proud of is that we have gender parity, and we have for several years now. That means half women, half men. That was a joke, Joe. That was a joke. All right. That's right. That's a good joke. So another passion of mine is philosophy. I'm not proud of it. It just is. So this is a phrase I heard in my 20s, and it really got me hooked. The unexamined life is not worth living. Someone brought up suicide earlier. It's kind of like, you need to examine life. If you don't, you might as well kill yourself. That's my suicide joke. Okay, that didn't go over well. I thought it was funny. So let's see, that tree felling. So it's 6 acres in Elliott, Maine, which is just a little bit north of Portsmouth. And I've been, for 30 years, it's been my weekend hobby. First, it started with removal of invasive species, and many of you have probably done that. So just imagine that over 6 acres. So that's why it took me 30 years. So at some point in the process, I get to this, which is I think of it as gardening. The photo on the left, you have 3 trees. There's 2 of them are sharing the same location. I need pine for my project, so I cut down the middle one there. So I think of it as weeding, except the plants are 125 feet tall, and it just makes it a lot of fun. And there's my sawmill. And here's the beginning of a kitchen addition. Those buildings in the back are not my house. That's my damn neighbor. Can't fix up his damn place. My building's on the left. So this is a kitchen addition, and that's wood from the property. Most of the wood that went into this was from the property. This is a really nice enclosure with European triple glazed windows, which are just wonderful. The point of this story is do a good enclosure and have your HVACs be simple, small, serviceable. So we got radiant in the floor. There's my pooch Milo. On the left, my old dog Daisy. She's not with us anymore. On the right, this is ash floor. I've never done an ash floor. This was my first floor. I cut down the tree, I milled it, I dried it, I milled it, I did the tongue and groove, I installed it. And I was nervous because each step I hadn't done before. And it came out great. It's still great 5 or 6 years later. Now we're getting to HVAC. You know, there's our kitchen exhaust hood. This is our heating thermostat. I like the thing that reminds me that it might be a T87, a Honeywell T87. That's what that is. And then in the yonder there, and this was my office. So when this AC system was installed, this was my conference room. And so we just kept the existing AC to air condition the new kitchen. And it's been great. Then over the mantle, it's hard to get retrofit ductwork in a 1800 house. But up on the mantle to the right is an outlet for fresh air. And then there's a close-up on the AC for the space. So back to, did somebody say soak crates? Did I hear that? I was going to tell that joke. Something from Socrates. This is from the Apology, but I like it better when he goes to the oracle at Delphi, and he's heard that the oracle says, you know, you Socrates are the wisest man in all of Athens. And the end result is he goes around and surveys a bunch of professionals, and they claim to know something, and he concludes, well, I don't know anything, so I guess I am the smartest man in Athens. So the basic idea that caught my attention with this is, at that time, I was in my late 20s, and I was having this realization in how much there is to know, and then how such a small part of that is what we know. And it just creates this opportunity for quite an adventure to just understand that there's so much to know, and you don't ever know nothing comparatively. So if that's good enough for Socrates, it's good enough for me. So integrated design. So I consider myself to be Joe and John Straub taught in terms of enclosures, and Mark Rosenbaum as well. And so there was a period of time, probably the last 20, where I invested a lot of time because I was interested, turns out, in enclosures. And so the integration with enclosures for mechanical engineers is a really good idea to understand enough. You know, in my kitchen, I just did as much as I could because, and I'm going to talk about this a little bit, I'm going to do as much with the enclosures as possible because that's where the comfort comes from. It's also where you can chop into your heating and cooling load. And there's not much else that contributes to reducing your heating and cooling load. It's in ventilation, you can have high performance energy recovery ventilator, but it's really the enclosure. In most buildings, I mean, single family homes are obviously external load driven, but there are exceptions, of course, as internal load driven buildings like data centers, that sort of thing. But most of our buildings are buildings for people. And so in that case, the cooling and heating load are associated with the enclosure. So moving right along, energy modeling, actual energy use. So it's generally understood, and it's already been mentioned a few times today, that modeling is for certain things and not for others. So it's not for predicting how much energy a building is going to use. We typically use it to meet the requirements of a program like Passive House or to compare alternatives. So here's a little case study. So we have with Passive House projects, we've gotten energy use information now, which is really helpful. Not everybody is interested in spending money on evaluating energy use, but owners are right now because they're getting their bills from finished projects, and in some cases, they're surprised. So this is a pretty nice geometry. It's pretty simple. Window wall ratio is reasonable. So it's good design from a heat transfer standpoint. So this is our mechanical system. Boy, you can't make a picture of HVAC equipment pretty. So we have VRF, air source heat pump, heating and cooling. We have a gas-fired domestic hot water system. That's the only use of gas in the building. And we have a DOAS unit for ventilation. And then in each dwelling unit on the right, that's a vertical fan coil unit. So that's our system. So here's our energy use. So the far left is predicted. That's what we said to the owner. This is what you're going to use. This is what you should plan for. It's about, we're a little over 30 EUI. The actual energy use is the next bar. So that's what we're actually doing. The owner was concerned that their amount of energy they were using was more than they thought it would be. And it is. We missed the mark by 8 EUI or so. And then the next bar is the WUFI model results. And we still do have projects where folks understood that the WUFI model was a prediction of their energy use. And so there's been some awkward moments at the end of projects because our experience has been that the actual energy use is running about twice the WUFI modeling for multifamily projects in Massachusetts. And then the far right is national average of 60 EUI. And so how are we doing? Let's see here. We're typically seeing EUIs that are low 30s. Oftentimes WUFI is estimating 20, high teens. And so the reason why we do estimates is in order for owners to put that into their pro forma. So they want to know how much money they're spending for energy. We've been doing that for years. So we take that as we have a feedback loop and we improve those calculations all the time. So we're currently recommending for, say, a typical 100-unit multifamily project in Boston, 30 to 40 EUI, and then multiply that times the cost, and you're going to have your cost of energy. So the, let's see, each one of these, the breakdown on predicted, it's the predicted breakdown. On actual, it's, that's what the next slide's going to deal with. How do we get that breakdown? For the WUFI, that comes from the WUFI model. And we don't know what the breakdown is for the national average. Yeah. This is a building that has heat pump, heating, and cooling.
Five times whatever the scope is. I'm just trying to understand how many DC per square foot per year is the load rather than what goes into the equipment. So if I just pick a number, 2.5 for the field feet, it's 2.5 times 5. So I'm just trying to understand the big difference there besides what people use in their apartment. No one uses it. Is the orange one. That's what you've got. All orders of bags, multiple different. So I'm just trying to understand that.
So Mark's question was, why is this presentation taking so long? So Mark's making a comparison between the energy use and the load, and we'll get a little bit into that in a minute. So this is a trick that energy managers use, where you take a look at actual utility data and you look at the peaks and the valleys and you chop off and understand what went where. So peaks during heating season, we're going to call heating load, and peaks during summer we'll call cooling load. And then the top, we have actual domestic hot water heating because we only have one thing using gas. So that is where our breakdown comes from on the previous bar. So one thing that's gotten, let's see, a little bit more prevalent or present is the cost of energy. So we're seeing the feedback, and we have owners in some cases who are surprised at their electric bill. Domestic hot water, the electrification of that is something that's now coming online with energy use, and I'm not focusing on that, but I can answer questions about it. And so in one case, we had a project where the owner thought they were getting a net zero building, and they thought they had enough PV on their roof to offset their remaining energy use. So we all understand that that's not realistic, but that's what the owner thought. And so they weren't too happy when they learned that that's not what they had. So we're having cases like that. In terms of cost comparison with gas, we check this as needed. So it ends up being multiple times a year. If we have a case of a building, we ask for the utility bill, we look at the utility bill. So we're always looking to understand what the cost of gas is, what the cost of electricity is. So in our neighborhood, Massachusetts, this is about what we're seeing right now. So, so these philosophical things that I'm sharing, they're things that I saw and have stuck with me for years. And so I'm going to share some heating, cooling, ventilation things that I saw and they've stuck with me. So this stuck with me, that relative humidity outdoors through the seasons isn't that different. So there's really good news here. You don't have to move to Florida. And the way you do that is you have a really good enclosure. You get a little higher humidity in the winter. You don't get nosebleeds. You don't have to move to Florida. Okay, that wasn't funny. Okay, so I just wanted to demonstrate that when you take outside air and you add heat, all other things being equal, your the amount of moisture in the air stays the same, but your relative humidity, the amount of moisture that the air can hold, that goes way up, therefore the relative humidity is down. And that explains why this is true. My wife and I, when we moved into our home in 1996, we both compared notes at one point and we learned that we both had nosebleeds. And we just patched up a few things with a little help from Henri Fennell here. Thank you, Henri. And we reduced our air leakage enough so that we had a minimum relative humidity and we were okay. So this is putting that same graph with relative humidity, and then it's basically demonstrating what happens when we take that air in January at that temperature, at that relative humidity, and add heat, and what's the resulting relative humidity. So I'm just trying to make a point there that it's dry inside your house in the winter, but the relative humidity is not low outdoors. So, but if you go outside and you're exposed to too much wind and sun, you're also going to die that way. So maybe you do move to Florida. Okay. All right, get a little laugh with that one. Okay. So this is, yeah, and no disrespect to Florida, but my father moved there, and then he would complain about me not visiting. I'd call him and he'd say, who's this? You know, and I was like, why did you move? You're the one who moved. So anyways, so this is a little comfort, little block here. And basically it's giving you an idea of what combination of temperature and humidity 8 out of 10 people find unobjectionable. And so let's see what this means to us.
Nailed it.
So ASHRAE minimum comfort zone. So there's our dotted line. We threw it in there, 20% relative humidity. So you can see that a bunch of months, January, February, March, and December, we're below that line. And you know it when you're in a space that's too dry from a human comfort standpoint. So I want to get into something else. So this caught my eye, which, and this, thanks to Passive House for tuning me into this. The interior surface temperature of a good window is higher than a not so good window. And so now we're talking about radiant loss. So radiant loss from your body, so radiant loss from you to surrounding surfaces that are lower temperature than you is you're radiating heat. And so the interior surface temperature of the exterior assemblies matters. It matters a lot to comfort. And so the other day we had a project where they were saying, okay, so triple glaze is just a little bit better than double glaze. So that means we should just use double glaze because that costs less. And I'm thinking, oh, yeah, so it may not move the needle if your window wall ratio is reasonable in terms of peak heat loss, but it does impact comfort. And this particular application was wheelchair bound individuals, and they require a little bit more to be comfortable. So this is basically comparing a couple triple glaze with a double glaze and getting at the interior surface temperature. The line across is the Fias min. And so this is where double glaze can have trouble meeting passive house requirements that are both take into consideration radiant, but also condensation risk. So the other guys had some formulas. So at lunchtime, I added one. Anyways, that's all. That's the only reason I put that in there. Wow, I got a clap even from over here. That's amazing. So when your enclosure is good, then you don't need distribution. Okay, some people say no. Okay, no, it's true. So we don't know perimeter distribution. We can go with something that's much more simple. So remember, we're talking about in the context of multifamily housing, but single family home, it's going to be the same thing, like I demonstrated with my kitchen. So rules of thumb really cause a lot of trouble. This is like the standard rule of thumb for peak heat loss in Boston, Massachusetts, as stated by people that do my job. And it's really high, right? 35, that might not mean anything to you, but if you compare it with, and this gets into our loads, Mark, we're less than 10 BTUs. So we're, oftentimes we're 4 times smaller than typical, and oftentimes we'll go into a situation if we're coming in after the fact, and we'll see that the enclosure has been done really well, but the mechanical system has been oversized. In the case of air source heat pumps, they don't work well. So in heating mode, they have to have a minimum load, and if they don't, they'll leak refrigerant by, so you're getting heat whether you want it or not. And on the cooling side, they'll short cycle, the coil doesn't get cold enough to remove moisture, and in both cases, you'll have compressors that are wearing out faster than they should because of short cycling. So now we're going to get into cooling, a couple of principles that struck me. Again, the rule of thumb. So 400, it's hard to separate a mechanical engineer from this rule of thumb. So it might be universal, maybe it's more than Boston. And sometimes we, this is really bad. Let's go with a 200 square feet per ton. But you do the load calc, and this is worst case. This is a corner apartment. It's got a roof load. It's got 2 walls, and we're still almost 1,000 square feet per ton. So oftentimes we'll see 3 times difference in cooling, actual versus rule of thumb. So that's not good. So in our industry, by peers, it's defensible that there's some oversizing, because intuitively, if you're cold in the winter, we intuitively think, well, the heat's not working. Not the windows are leaky, something like that. So there's in some ways I sympathize with oversizing, not dramatic oversizing. So here, key, we right size, make it small. And now we're going to get into a little bit of ventilation. So obviously this is just a psychrometric chart. It'll look like I know this. So one of our criteria, and this is super critical, is we have small, simple, serviceable. So the serviceable part, we want to specify things that are really high quality, both in the product itself, but also the likelihood that the product will be supported for the life of its installation. And so you got to pass those criteria, those 2 criteria for us to specify the product. So let's see here, simplification of the apartment design. So on the left side, it's a studio. And so what we like, so oftentimes there's been frustration. Just tell us what the HVAC system should be, the system. So what we've landed on is the vertical fan coil. We have very brief ductwork. Doesn't have to be at the outside wall. In the studio, it is shown at the outside wall. And it requires very little ductwork. And it also can be the terminal unit for a refrigerant-based system, for a condenser water-based system, for a chilled water, hot water baseboard system. So you can conceivably design your apartment, get a standard design, and when you move from one building to the other with a different system, it'll be suitable for different systems. On the ventilation side, on the left, we've done a pretty good job simplifying that ductwork, but it could be even more simple. And on the right-hand side, it's okay. But oftentimes we are asked to distribute ductwork above or within a rated ceiling floor assembly. And it just seems like a bad idea, but there's pressures for ductwork to be distributed in apartments for different reasons. So in this case, we've come away from the outside wall. Let's see, on the left, we have a 2-bedroom. So we have the ductwork in the ceiling. I can tell it's in the ceiling floor assembly. We have supply grills in the ceiling, and then you've got the red as the ventilation ductwork. So in this case, we have a drop ceiling. So we have a horizontal fan coil unit with duct distribution and sidewall registers and grills, and then the ventilation is over the top of that in the ceiling floor assembly. Serviceability of basically anytime you tell me that you're going to have a piece of equipment above a ceiling, I'm going to tell you that the serviceability is unacceptable. And this is like disaster. On the left, we have a above ceiling energy recovery ventilator. We have a vertical fan coil. In the blue duct, or the light blue or cyan, is ductwork that's connecting us to the outdoors. So what that means is in the winter, we have 2 ducts that are a condensation risk, and which means a water damage risk. So that's not desirable. This is out of hand. Okay, ventilation. I love this one. So David Hume. So let's see, he was, his thing was skepticism. And one of the things he wrote a lot about was causality. And we tend to, as humans, assume that if patterns emerge, like the sun rising each morning, that's necessarily causation, that the sun rises in the morning. There's cause and effect. And so he's going through this really long explanation that's super rational. And I'm like, wow, this is great. I'm buying it. I never thought of this before. And at the end, he finally says, he must have had a bad day or something. He said, oh, but at the end of the day, reason is a slave to the passions. I'm like, what? So we all have to kind of accept this notion that we may think we're rational and clear mind, clear thinking, that sort of thing, but not according to David Hume. So one thing we've been trying to promote is in multifamily, the 4-to-4s are very tight. So delivering air ceiling down is not a great idea because you don't have enough vertical distance to get that air straightened out. So what we really want to do is sidewall supply, both for heating and cooling and for ventilation. So what we're showing here is a sketch where an owner came and said, geez, I don't like passive house. And I was like, oh boy, that's not good. But their experience with the ventilation being decoupled is that they were having cold drafts and it was coming out of the ceiling. So there's a few things that we can do to mitigate that. That's high sidewall. And before I move on, here's some benefits of central ventilation. It's serviceable. So what I do like is something where you can stand like me, hold your hands like this, and you can work on the piece of equipment. That's serviceable. Also, if we take these out of the apartment, we have 4 or 5 of these on the roof instead of 100 or 150 pieces of equipment in apartments. Easy to replace. Rent a crane. So each 20, 25, 30 years, you replace the unit. So there's a little history of ventilation. So 15 or 20 years ago in Massachusetts, it's still happening today, is the makeup air for the kitchen and bathroom exhaust gets drawn from the kitchen and the bath, and then makeup air gets dumped into the corridor. Now, the code hasn't allowed the corridor to be a way to convey air in decades, but it's still happening in new designs today, that this method is being accepted. Our experience has been that code enforcement officials, for whatever reason, don't touch ventilation. So this is a migration of distribution where we now have the ductwork going down the corridors, and for years, not years, but maybe 5 years, we were allowed, without being VE'd, to get the supply inside the apartment door. And then things changed further, and now we didn't have to stress it. The code did, and the programs did. So now we have supply air into each occupiable space. So what this means is when we have the DOAS on the roof, we have a lot of teeny-weeny openings moving teeny-weeny amount of air, exhaust and supply. So this is a big con in terms of simple for central ventilation. We have it's a relatively simple ductwork distribution system, but what's going on in that system is not so simple in terms of pressure, flow, that sort of thing. So we do end up with a little trouble. I'll get on to the troubles here in a minute. So what we do with the DOAS, we've got a really high-performing heat exchanger, and then in the winter we temper to 70. We don't want to temper higher than that. The way for us to do this accurately is with modulating electric resistance. And then in the summer, we dehumidify. So we get the humidity at the source. And then that combined with the right sizing the air conditioning system in our climate is enough of a combination that we don't have high humidity issues in the summer on our projects. Duct sealing, seals. Thanks, Nicole. Nicole laughed at her own joke. You can do that. Okay. So AeroSeal. So we've been an advocate of a proponent of AeroSeal. It's in our basic spec. So what we did with this complex duct distribution system, we said, okay, we got to AeroSeal the bejesus out of this. So that's what we endeavored to do. And we put a lot of time and effort and put up with a lot of pushback, just working to specify duct sealing requirements and duct air tightness requirements that would be and could be done. So another difficulty, I forgot my car damper samples in the car. So the car damper. So this is just for scale. This is a 4-inch damper. And what this is CAR stands for constant air regulator. So it's a regulator. So at differing static pressures upstream, the car damper modulates, and this is what you could have experienced yourself. The car damper modulates and either opens the car damper a little bit or restricts the car damper to get the same flow at a range of static pressure. So ignore this on the left, that doesn't make sense. But what I do want you to see is under preliminary testing, we've got design rates and we have preliminary measured rates. And the point of this slide is that use of hoods early on, this is 2013, 14, 15, we couldn't get reliable information. And so what we expressed was a preference for give us the static pressure. And, oh, by the way, the gentleman center bottom looks like Joe. It must be his son. So, so we were satisfied with static pressure, juxtaposed with the manufacturer's data that showed the performance of the car damper at a range of static pressure. And this is just a throwback, Home Energy Magazine. And this next thing turns out to be very controversial. But Home Energy Magazine was something I read to go to sleep at night. It was just a magazine that I really enjoyed. And so doing a little search, this photo popped up. So it's not a surprise that Joe was involved in this. So in this 2003 research, which was also an article in Home Energy Magazine, it just pointed out something that turns out to be very disruptive, which was that, oh, your hoods aren't that accurate, and which is bad. And by the way, if you take a garbage bag and put that over the opening and a stopwatch, you'll do as well. So what do? I put together my bag, and we go down to an early project, and there's frustration because we're talking about low flows, but we're also talking about flows that aren't particularly laminar because they've just come through this regulator. So they're mixed up and low and hard to measure. So with our bag, we were able to get, good, in our trials, we were able to get similar numbers. That's the point here. So we're plus or minus 6% in our bag measurements, which is like, wow, this is great. Not so great, turns out. So this is the car damper manufacturer's data, which is according to an EU test procedure. The US does not have a test procedure for car dampers. So what I highlighted in green is what we oftentimes are in and around, which is a 75 CFM setting. And so this car damper has multiple settings from 15 to 85 CFM. So you can set it to the design CFM in the field. And so typically, like I said, we're 15, 20, 25, 35, that sort of thing. So what I want to point out on this is between a static pressure of 0.12 and a static pressure of 1.2, we have really consistent performance in terms of the flow rate at a very wide range of upstream static pressure. It's like magic. So more recently, I think as Passive House became code required in Massachusetts, we have more projects going on and more people participating in more projects. And so the car damper thing came back up again. So here's another knowledge is power. So this gets misinterpreted, but for Francis Bacon at the time, it was a scientific revolution. He was understanding that in order to understand something, you do it through the scientific method. At that time, if you went to Cambridge or Oxford, apparently, you were learning from the wise old people. And so now we're talking about a revolution in what knowledge is. And then the idea was that we understand the laws of nature, and we'll be able to, as humans, we're able to take that understanding and apply it for good, like maybe sanitation, so other things at the time. So that's what knowledge is power. It's basically a articulation that we can take our understanding of how the world works and put it to use, and it's powerful. So ResNet. So the FIAS, and I'm not a technocrat in understanding this, but the FIAS program leans on Energy Star. Energy Star leans on ResNet for understanding how your ventilation system is performing. And these are the different methods that are listed in ResNet 380. There's a couple that we eliminate because they require something that we can't provide, like access to a straight duct. Typically, the duct is inaccessible above the ceiling. But we do have these other methods that are listed in ResNet, and two of them, one is the bag inflation. It made the standard. And I was shocked when I learned it. I don't know if Jonah's in the room, but Jonah said, James, it's in from his office. It's in ResNet 380. I'm like, what? The bag? Yeah, made the bag test. And then we also have this air measurement station. I'll get to that later. So here I am. This is fairly recently, and there's Sarah, who's here today. And we've gone to a project to do our bag inflation. Oh, that was supposed to play a little video right there. No, that's not it? Okay, all right. So we were there with the tab contractor, and we were getting our bag results, and he was getting his flow hood results, and then he was also giving us static pressure results. So I like this triangulation. You know, how do you understand what's actually happening? Well, if you have like 3 different test methods, and maybe they have some margin of error, then boy, you probably gain some confidence to understand what's going on when you get the range of test results. And so we did. I remember the tab contractor was pretty excited that he was getting the same values as we were getting with the bag, and the static pressures were within the range of the car damper. So I come away from that thinking, wow, this is great. And so here's the actual ResNet, which is funny to see something like a garbage man stopwatch put into technical terms. So I got a kick out of that. Okay, here's the video. Now, if the audio, I could only set the audio in one setting. And I had a chainsaw video, and now I have a garbage bag inflating video. So you can't hear the bag when it snaps full. All right. You did. You could hear it. Anybody want to hear that again? Oh. Okay. So that's a pretty nice thing, because the person on the stopwatch, it's kind of like if you were timing the 100-yard dash, and this is how it used to be timed when I was in high school. So you'd see the person coming, and bam, they cross the finish line. So the same thing with the garbage bag. It's a snap, so you're ready for it. And that's one of the ways we can get really accurate information. The other thing that's interesting about the bag is our hood takes an indirect measurement. The static pressure is also an indirect measurement. The bag is a direct measurement. Doesn't matter. No, I'm just kidding. Yeah. Yeah. You have to know that, and then you have to do some math, but it's math that even I can do. Yeah. What you want to do is, I don't know if you guys have, it's your guy. You probably haven't changed the kitchen trash can in a while. But the thickness of the garbage bags are like so thin, it's unbelievable. So, the standard does require that it fills up within a certain range of time, which makes sense. You don't want it to be too fast, you want it to be too long. But in terms of the garbage bag, you want to get a nice thin wall garbage bag. Otherwise, you might be accused of creating some sort of back pressure. So again, we're getting good trials. Okay, so you've seen this before. I never knew so much. I never knew ResNet existed until having to really get into the weeds on this. So Ian, 2003, I just remembered him because I had this love affair with Home Energy Magazine. And so I've been emailing him. So one of the things I emailed him recently was, geez, it looks like ResNet allows for a static pressure method. And it looks like if we think of the car damper as a measurement device, it works perfectly. So I shot him an email, and he got right back to me and said, yes, so long as your car damper tolerance is within plus or minus 10, which it is. So now we have a ResNet approved method for static pressure. We have a ResNet approved method for bag inflation. We have a ResNet approved method for hoods. So we've got a lot of tools at our disposal. So here's the combination I'm talking about, which is, I think you rally around and you get pretty good confidence in what's going on with your ventilation system. So one of our challenges is that, let's see. So, and I think this was emphasized this morning with Bill's presentation, which is that ventilation is not, it's not exact. You know, sometimes the outside air is not helping you even. So we don't want to get too hung up on, say, if we've designed 20 CFM, that, you know, it has to be exactly 20. And if it's 19, it's no good. You know, it fails. No, 19 is not a fail. Think of it as hand grenades and horseshoes. Getting close, you know, still does the trick, or you still score some points at least. Another death reference. So what we found is that in the program, let's see here. Well, this is where Fias is saying this is the process for, you know, what's acceptable for testing. And so it's ResNet and it's Fias approved. So they say here that ResNet's an approved method. So I just want to close that no, ResNet is what we're looking at to understand what's going to count in terms of ENERGY STAR compliance. So there's this thing where you say what the design CFM, you put in the verified amount, and then it spits out not acceptable. So that's not good. That needs to be different. It is acceptable. Here's another formula I put up there. Never seen it before in my life. This is a way of estimating the combination of various errors. This is the first, I don't know anything about this. It's like the sum of squares and the square root of that. Don't ask me why. But what it does is the errors aren't additive. You know, it's not 1 + 1 + 1 + 1. It's ends up being 1 + 1 = 1.2, something like that. So because the chance that you're off way left with one error might be that the next error's off to the other way. So they kind of juxtapose each other. They offset each other at some times. So I'll have to ask the two professors more about this later. So here's an example of taking tolerances. We have a 10% plus or minus with the car damper. We have a tolerance associated with the measuring device, and it goes down a list. And the point is that we can't be talking in terms of 19 or 20 because the tools and the actual device isn't that accurate. And with ventilation, what we're aspiring to do is get mechanical ventilation systems to work. And so that's where our objective is. So you can see where plus or minus 16, you can see that we're going to be general about that. So Fenway Park, the key is to be in the ballpark with ventilation. We want to be in the ballpark. It's not a binary thing. Either you have ventilation or you don't. And the reason why I bring all this up is because we've, I think it's a combination of things, but the resistance to use of car dampers is strong. And I understand why, but if we had a different solution, we would do it. Now, what is possible is to move the ERBs back to individual dwelling units, but then we have challenges of, can we get the space we need? Can the unit be on the outside wall in order to get rid of a water damage threat? We have additional penetrations of the assembly, which are to be avoided. We have a serviceability issue. So it's not passing our small, simple, serviceable, and neither does this particularly well in terms of the extensive ductwork. But we'd like to not have, if you have 100 unit multifamily, we'd like to have not have 100 pieces of equipment that need service 4 times a year. That's not going to happen. We'd prefer to have something on the roof, and there might be 4 of them instead of 100. So that's our preference. So that's it. So I think I do have time for some questions or comments, Joe.
A quick question. In your single rooftop units, your corridor distribution, and then the branches to each suite, are you fire dampering when you leave the corridor and go to the suite?
Give me the last part. I didn't hear the last
Are
part.
you fire dampering
Fire dampering.
separation between the corridor trunk and the branch in the suite?
Where there's a smoke fire damper is where we're dropping in a shaft, a rated shaft, and where the ductwork emerges from that rated shaft at each corridor, each floor, that's where the smoke fire damper is.
So you have no smoke fire damper at the entrance to each suite?
No, because we're not interconnecting the corridor with the apartment. There's no interconnection of air volumes there, so we're not required to have a damper at that location.
Interesting. The last job I was on in Vancouver, that was all done, and the leakage in those dampers was just outrageous.
Fire
So
smoke dampers?
Yep, and
Okay.
you're saying that it's not required. I'd love to hear further on that, because obviously there's confusion interpretation of that requirement.
There's some people in this room that can talk probably better than I can, but I know that we don't have any smoke fire dampers where we go from the corridor to the apartment. Thank you. So under a certain amount of square inches in the penetration, we don't need the fire damper. Thank you.
Why is there great resistance to the use of car dampers? Right?
Christ? Was it Christ? Well, there's someone offered extra static. The 0.12 is the static that you need. So you have a minimum static. That hasn't been part of the opposition. So yeah, that hasn't been an objection. What's been an objection is it's hard to get accurate measurements with the flow hood, which is true. And the flow hoods tend to underestimate a little bit, but then they can also be high and low, and they can be inconsistent. So there's some resistance to using these other tools, the bag and stopwatch and the static pressure. So those tools have not been implemented by many people. So they don't have that triangulation going on. So they have the hood. And then combine that with the accuracy thing, the tolerance thing, where you have to be, if the design value is 20, which is the design value is what we say, right, on our plans. If the design value is 20 and you get 19, it's like rejected. So there's that problem too, of precision, where precision is not appropriate.
Just to further up on fire damper requirements.
Yeah.
In Canada, the demarcation was 19 point something square inches, which is a 5-inch duct. However, if you ask the NBC on that question, they don't know the history of that having been slipped in or the limitations on its application. But it originally had a limitation of how many inches above the floor that penetration could exist. So I have yet in 30 years to get an answer to that question in Canada.
Thank you. So we got 26,000 units that are not designed properly. I'm screwed. I'm not going back to work.
Or North America.
He said, Joe, to clarify, Joe says it's North America.
I believe it was 50% for the 11th province.
So, James, I feel like I need to push back a little bit on the EUI prediction for multifamily.
Okay.
We've got a database of 10 or 11 multifamily projects in the Northeast that are coming out between 20 and 25 kBTs per square foot for utility data. And PS has a big database that, is all pretty close to WUFI. So I guess, my question is what's happening in that project? And one of the things that we've seen is WUFI modeling can greatly underestimate hot water usage. And also, there can be issues with recirculation losses and that kind of thing, which can push the gas use up, which can be a big piece of it. But I feel like it's unfair to say that we should expect 30 to 40 kBTUs per square foot out of a PS multifamily project.
Yeah, so Galen's a MEP, FP engineer in Virginia, and I respect him a lot, and he's better than I am because our jobs aren't performing that as well as yours. And so, yes, domestic hot water seems to underestimate. I think also there's some black box essential things in the WUFI model that I think might be the air infiltration might not be as high as it actually is through door openings and window openings and things of that nature. This isn't just one project I'm talking about. This is a pattern of multiple projects. So this is a representative project compared to our, it's a representative project of what we're seeing.
You get the last question, young man. Yeah.
Young man, I just hurt my back this morning. Yeah, it's me again. What do you do in areas where you need dehumidification for each unit?
Dehumidification. So what we've arrived at with a lot of, completed projects is if we design the air conditioning system properly, this is Boston. If we design the air conditioning system properly and we get dehumidification on a call for cooling, and we combine that with getting the humidity at the source in terms of the ventilation air, we've done enough dehumidification with those two methods for removing humidity.
So what about for states who name their high schools after Confederate generals?
Yeah, so that's a different
I
story.
think that strategy is going to work in the South. We have a lot of low sensible,
Yeah.
high latent days,
Yeah.
and bringing in ERVs. ERVs are not dehumidifiers.
Right.
You got to get rid of that net moisture.
Yeah. Now we're slowly becoming like a southern state.
Yeah, it's coming up to you. Thank you.
No, this doesn't apply in Florida. I can imagine that there's a requirement for dehumidification. Obviously, it's different in DC and Florida than it is in Boston.
All right. Thank you.